Starting. I'm starting. So what I want to transition to today is I want to finish the discussion of the Axion, a very brief discussion of the Axion, move on to thermal dark matter candidates, which you know very commonly by their name of WIMPs, and then move on to at least introduce you to what are some of the motivating quote-unquote anomalies that cause people to develop non-standard models of dark matter. So, interesting. Aha. It's here. So let's start by going back to the Axion. So remember, the Axion was a particle that was introduced to solve the strong CP problem. So we had this kind of an interaction in the Lagrangian, and the idea was that this scalar field A here should shift in order to cancel off the theta bar parameter. And the way you should think about the cosmology of the Axion, one thing that we talked about last time was the fact that an oscillating scalar field behaves as dark matter. So but you still want to think about how the history of the cosmology of the Axion unfolds. And so the way the conventional cosmology of the Axion goes is that there is some potential that at high temperatures looks like this. So this is your finite temperature, high temperature potential. Then at some intermediate time, you develop a spontaneous symmetry breaking and you acquire VEV. So the field will settle at some point along this Peccei-Quinn symmetry, and you have a Goldstone boson which allows you to move along this direction, and this Goldstone boson is A. And we can effectively identify this decay constant with the VEV of this field, more or less. Then, at very late times, you go through the QCD phase transition. When you go through the QCD phase transition, you realize this is not a true Goldstone boson, but a pseudo, and the potential develops some sort of a preferred minimum that is oriented to cancel off this theta bar parameter, and it will cause the Axion to settle there, and now it has a quadratic potential that will cause it to oscillate. So one of the basic questions you can ask about this process, one of the things we said was that the decay constant that you want in order to get dark matter is around 10 to the 12 GeV. So one question you can ask then is, how does the history of this process unfold? And one of the critical questions that you can ask is whether or not this process occurs before inflation or whether this process occurs after inflation. So if the Peccei-Quinn symmetry is broken after inflation, then the value that the field will actually roll off to in that second step there will be random in each different horizon of the universe. And so you'll have on order a roughly pi value for the Axion. So f over a will be approximately pi. And so if you remember, this was the expression for the amount of dark matter today in the form of axions for fairly conventional models. So this theta takes on a random value in the universe, and so you get a value which is overall pi. And so this is roughly the order of magnitude that you want to get the dark matter. But if Peccei-Quinn symmetry is broken before inflation, then this initial angle is one value in whole universe. Because you take this one patch, you acquire a VEV, you sit at one particular orientation, then you inflate that patch and you stretch it out. And so, in principle, this initial angle can be anything. Indeed, in particular, it can be very, very small. So I can raise the value of FA here above 10 to the 12, and ordinarily you would think that by raising the value of the decay constant, I would overclose the universe. I would have too much dark matter. But in principle, I can lower theta I and still have the appropriate amount of dark matter. Now, obviously, you'd allow me to say raise this to 10 to the 12, or sorry, from 10 to 12 to 10 to the 13, say, without getting too up in arms, because that's a 1 in 10 tuning. And maybe you'd allow me to raise it up to something like 10 to the 14, and it would be about a 1% tuning. But if I start raising it up to values like M Planck or M gut, then this becomes very, very precisely tuned. But you can have a tuning for the what's referred to as anthropic axion. That it might be that the reason why we have such a small amount of dark matter is just because if there were much, much more dark matter, then there would not be enough baryons to form stars and interesting structures in galaxies. So it could be that we actually do live in a universe where FA is very high, but that we are selecting universes where theta is very small in order to have an appropriate amount of dark matter. And the reason why I mention this is that this makes particularly interesting questions of large FA, going to very high values of FA. So last time we discussed the fact that stellar cooling places limits on FA to make it higher than 10 to the 9, and presently there are direct experiments looking for axions in the range of 10 to the 12. But you then have a separate question, which is, are there any experiments out there that can look for decay constants which are much higher than that, closer to the Planck scale? And so just before we segue off of axions, let me just point you to one, I think, very, very nice result by Arvanitaki and Dubovsky. And what they looked at is black hole spin down. So you have rotating black holes, and you have the ergosphere region around them where you can actually take energy out of the black hole. You can transform the angular momentum of the black hole into energy. This is the famous example of throwing garbage into a black hole and converting it to kinetic energy to power a civilization. But you can get energy. You can convert the spinning of the black hole into energy. And the statement of these people was that if you have a very high decay constant, then the Compton wavelength is comparable to this size, which means that you can actually have a resonant process where once you start producing one axion, you can just spontaneously convert some of the rotational energy into an axion. And then, because it's a boson, this process will be resonant, and you can actually spin down the black hole by producing axions. So if that were true, if there really were a string scale axion or a Planck scale axion, then rapidly rotating black holes of the appropriate size would convert their energy into axions, and you would not observe them. So they have observed rapidly rotating black holes at a wide range of masses, and these authors then convert that into a upper limit on the axion decay constant of about 2 times 10 to the 17. It's a very interesting result. Yes? It's this. So, any questions about this? Because I want to move off of axions and move on to thermal dark matter. Okay. So the next category of particles we want to discuss are thermal particles. So the idea there is that you have some process in the early universe that converts ordinary matter, by which I mean standard model matter, into dark matter, and vice versa. And the way this is going to work is that there is this is parameterized by an annihilation cross-section. Which we write as sigma v, sigma times velocity. And that this is going to tell us how efficiently dark matter converts into standard model. So dark matter in the early universe is annihilating into the standard model. And as you recall, the number density for a non-relativistic particle scales like e to the minus m over t. And so if you look at this process, what would happen is that you have if I go to very, very early times, the ratio of the number of dark matter, say, versus the number of photons would be order 1 for a while, right? They're basically the same number, set only by their degrees of freedom and spin. And then once you get to some temperature, where the temperature is approximately equal to the mass, this exponential is going to kick in, and you're going to lose all of this dark matter. And if this system stayed in equilibrium, the dark matter would continue to annihilate until there was essentially no dark matter or none of this relic particle left at all. But that won't happen because eventually you'll get to a situation where there are not enough dark matter particles around to find each other to annihilate. So if you have a very low cross-section, then at some point you'll break off from equilibrium. And if you have a very high cross-section, then you'll stay in equilibrium for a very long time, and you'll end up with a much lower density of dark matter. And of course, in between, you will have something in between. And so for some value, for any given dark matter particle, for some value of this cross-section, you would expect to have the appropriate amount of dark matter, because I can tune the amount of dark matter that's left today just by varying the annihilation cross-section. So I want to take you through a very rough derivation of this. And the sort of classic one that you'll see is in Colden Turner. And I personally find, even though it's very complete and it's a nice reference, I think it misses out on some of the nice intuitive aspects of this freeze-out process. So let me take you through a slightly more sketchy one, where the appropriate physics is still there. So the process we're referring to is freeze-out. That is that you have a system which is in equilibrium, and at some point that system stops being in equilibrium. And the condition for freeze-out is that the number density of dark matter times sigma v should be equal to the Hubble constant. And so n sigma v is just where this is the annihilation cross-section. So n sigma v is just the rate at which any dark matter particle floating around in the universe annihilates with some other dark matter particle. And the Hubble constant, remember, is the rate at which the universe changes by an order 1 size. The reason that this is the condition for freeze-out is that if you think about these in terms of time scales, if dark matter has not found another dark matter particle to annihilate within 1 Hubble time, at that point the universe has essentially doubled in size, meaning that it has gotten more diluted, meaning your probability of finding another dark matter particle has gone down considerably. So if you wait 1 Hubble time and you haven't found another particle to annihilate with, you're never going to find another particle at leading order for the rest of the history of the universe, assuming the cross-section scale in the ways that I'm describing. So the simple observation to simplify this process is to note that at leading order, the temperature of decoupling of this freeze-out, actually let me call this freeze-out, is equal to the mass of the dark matter particle. And this is only true up to factors of something like 10. So I can actually parameterize this with some other number x, which actually makes this more accurate. But the important thing to understand here is that x is some number which is like 10 or 50. It's not an exponentially large number. And the reason for that is that you have this exponential there. So as soon as you get into the range when the temperature is below the mass, if you're 50 times, if the temperature is 50 times below the mass, then you're already exponentially suppressing the number density of dark matter particles. You don't need to go exponentially below the mass of the dark matter particle in order to stop this process. Getting some order 1 factor or order 10 factor below the mass already exponentially gets rid of dark matter, and so you know that this is about the scale of Freezeout. So, so I can then solve this, right, because I know that the number density is just equal to h over sigma v, and h, remember, is approximately t squared over m Planck. And as we just said, this is the mass of the dark matter particle times some number x. But that's what the temperature of, what the number density of dark matter is when it freezes out. And what you actually want to know is, what's the density of dark matter around today? So I need to take this number density at freezeout. So I want to know the number density now. And so I want to take the number density of freezeout and basically imagine that I'm taking that universe and I'm expanding it by some factor. So remember what we said was that the temperature scales like A inverse. So we can use the temperature of the photon bath as a proxy for the expansion of the universe. So if I want to know the amount of dark matter, the density of dark matter now, I just take the amount that was then when it froze out, and I redshift by this expansion factor. And as I just said, this is just this factor, right? And so if you then have the number density now is equal to, let me put in the expression that we have for the number density of freezeout times this redshifting factor. T now is whatever T now is. And the temperature then, as we said, is m cubed x cubed, cubed. But this tells me the number density now. But the number density of dark matter particles now is not actually what I observe. What I observe is the energy density. So what I really want is rho now, which is the mass of the dark matter times the number density. And so what you see then is that I can cancel off this mass, and you're left with an expression which is quite simple. So the energy density now in dark matter is just dictated by the temperature, the photon temperature now, divided by m Planck over sigma v times this number x. And I am being fast and loose because I'm not worried about the fact that as the universe expands, entropy is dumped into the photon fluid, and that's going to change this by an order 1 factor. But that's a calculable factor which does not depend very much on the dark matter mass. Almost all the dynamics is captured here. So this is the very, very important observation that the energy density now is almost determined by sigma v. Okay? So when you observe the energy density in the universe, you're actually making one observation on your model, and that observation is just on the annihilation cross-section. So you're learning one piece of information about the dark matter. So what is that cross-section? Well, what do we know about dark matter? there's a very, very simple way to calculate the cross-section that you need, and that is to note that there was the temperature of matter radiation equality. Temperature of matter radiation equality is when dark matter had the same energy density as radiation, and that happens at a temperature of about 1 electron volt. So I can, instead of asking what the density of dark matter is now, I can ask what is the energy density of dark matter at matter radiation equality. And the energy density at matter radiation equality, using that expression up there, so T to the fourth is the energy density in photons. And so this is just the statement that at matter radiation equality, the density in dark matter should be equal to the density in photons. And I can repeat this exercise from above. And again, I can cancel off, as before, a lot of these m chi's. And so I'm left with this expression, which is that temperature of matter radiation equality is equal to the temperature of matter radiation equality to the fourth, right? So I'm just saying that the energy density in dark matter is equal to the energy density in photons. And then this allows you to solve precisely for this cross-section. And you find that the needed cross-section is the geometric mean of the Planck scale and the temperature of matter radiation equality. But the Planck scale, the geometric mean of this number here is of the order of the TeV scale squared. Right? That is approximately the geometric mean that we're talking about. So, and now it does depend a little bit on this parameter x, but right now we're talking in we're talking very order 1. And this is what is referred to as the WIMP miracle. And it's that if you take any old particle in the early universe and you put it in thermal equilibrium and you ask how much stuff should be left around, you end up finding out that the amount of stuff left around is the appropriate amount as long as the scale that sets the scale of the cross-section is essentially the weak scale. So particles with weak scale cross-sections end up giving you the appropriate amount of dark matter. And since we separately have motivation for new physics at the weak scale, this is then taken to be some very, very interesting sign that there should be new physics, that this is a really well-motivated model. Now, you should be very, very careful because cross-sections that depend on the weak scale, there are all sorts of parameters like alpha, pi's, and the scales. This is a very, 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 very loose miracle. This is not that good of a miracle because you can vary the coupling constants in cross-sections, the scales in cross-sections by several orders of magnitude, and most people would still claim success and be like, oh, so if this, instead of the temperature matter radiation equality were, say, several orders of magnitude lower, I think people would still claim that this was a successful miracle. So you should take it for what it is. Questions about this? So why do we care about this? Why do people spend so much attention on this? The real reason is that this is a very, very detectable model. And I'm going to draw for you a diagram which if you've seen it 1,000 times, but if you haven't seen it, then this will be the time you see it. And that is that if this is the process that keeps you in thermal equilibrium in the early universe, then you've just measured the size of this to be approximately 1 over the weak scale. So you've measured something interesting about the interactions of dark matter. And what you've actually measured is the size of this diagram going this way. But once you know the size of this diagram going this way, you can be very, very hand-wavy and make arguments that you can rotate the time axis, and you can think about processes that would go this way, and you can think about processes that would go this way. And the way then this is interpreted is that you now have 3 means of actually accessing the dark matter particle. So what are they? Well, let me label these as 1, 2, and 3. And these processes are 1, what's referred to as indirect detection, which is dark matter annihilation in the halo, or in just around galaxies. So the idea is that dark matter annihilation has stopped. It's no longer in thermal equilibrium, but it could still be going on at a non-equilibrium rate. And if you look out at the Milky Way, if you look at the center of the galaxy, the annihilation products of dark matter that are out there, and you might be able to observe them. So these could be a lot of things. They could be photons, they could be neutrinos, they could be charged particles, and people look for all of them. 2 is what referred to as direct detection. And that is an underground experiment, generally, where you hope that the dark matter particle will come through and you have some nucleus, and that nucleus recoils. So you don't actually know if it's going this way that this standard model particle on this side of the diagram actually is a quark or a gluon, something that would actually give you a direct contact interaction with the nucleus. But in many models it is. And so if this kind of a process is there, wind can come along, smack the nucleus, deposit some energy, and you can look for that, and that hopefully will be ability for detection. And then lastly, I'll write it over here so I don't have to change the board. You have colliders. We heard some about this yesterday for electroweak models, what you can think about. But the idea is very simple, that you can now take ordinary matter particles, put them together, and they'll produce dark matter particles, and you can look for that. Now, that's obviously a really, really bad signature. Standard model goes to nothing. So the actual processes that you look for are missing energy processes, where you have to produce something else. Either you produce some heavy particle that then decays down to dark matter, which is a bit of a cheat from this diagram, or you look for what are called monojet or monophoton signals that I'll talk a little bit about in a second. Yes? Is there any special reason to do a direct detection underground? Yes. The reason why you do direct detection underground is just because of backgrounds. If you do a rough estimate, you'll find that for a particle with a weak scale cross-section, with the energy density that we believe is around us, moving with a velocity which is roughly the virial velocity, you'll find that you're talking about, for kilogram-sized experiments, you're talking about an event a year-ish. So that's very, very low, and you have to suppress backgrounds. The kinetic energy, I should say that the characteristic velocity in the halo is around 10 to the minus 3. That's what the velocity is roughly locally. So if you take a weak scale particle with moving at this kind of velocity, the kinetic energies that you have available to deposit are sort of the order of keV. And there are a lot of radioactive decays that are in that energy. Cosmic rays can come in, produce muons that can then deposit energy. So you really are trying to shield your background. Even if you can discriminate against it, tails of backgrounds can be really bad. And I will talk a bit more about direct detection experiments later today. Other questions? Yes?
When you mean annihilation in the halo, you mean the halo that surrounds the Milky Way, or the halo that surrounds the galaxy?
Both. So this could be happening in the halo surrounding the Milky Way, and then you could, for instance, I could look for dark matter annihilation from, say, the galactic center, for instance. That's part of the dark matter halo that is holding together Milky Way. I could look for dark matter annihilation in charged particles that would be coming from all around us. That would be coming from the local halo. I could look for gamma rays just as I look away from the center of the galaxy. So you can really look anywhere, and different types of directions are more sensitive for different types of models. Other questions? Yes?
If you're only expecting like one event a year, is that enough statistics to say it's not like a neutrino?
Yes, you can calculate the rate that you expect for neutrinos. And the rate for neutrinos, unless they all of a sudden had very, very new interactions, which would be, of course, just as exciting, if not maybe more, is about 2 orders of magnitude below the current sensitivity of experiments. What you're really worried about is that if you only have 1 or 2 events, that you always run these experiments with an expected background of 1, because if you run it with a lower expected background, then you're overcutting, right? Because the more you cut away background, the more you're also cutting away signal. So you kind of run it on the knife's edge. And so sort of 1 event-ish is not good enough, because that's kind of what you usually expect. But then the idea is you'll keep running, you'll build a bigger experiment, and you'll up your cuts, and you'll be able to improve your signal to background. But I think that people would want, well, different people want different things. Be really convinced you'd probably want many, many events in multiple different detectors. As we'll see, we already have many events in multiple detectors, and that's not already yet convincing, but we'll come to that. Other questions? Okay. So I think that in thinking about WIMPs, it's really good to start with a canonical model that you can think about. And for me, the best canonical model is to take a doublet with hypercharge, a Dirac fermion doublet, doublet under SU2 with hypercharge plus minus 1/2. So you'd recognize this as a Dirac neutrino, or you could call this a pure Higgs xeno. You could call this an inert doublet if it were a scalar. I'm going to choose it to be a fermion. And so what is the exercise that you go through then? Well, the first thing that you do, if you're studying a model of a WIMP, is to ask the question, how is it freezing out? So what is the process that keeps it in equilibrium in the early universe? And so for a particle like this, the dominant annihilation channel is into weak bosons, W's and Z's. And you can calculate the annihilation cross-section where tangent TW is tangent of the weak mixing angle here. And this is what you get. And so then you can ask, all right, well, I know what the number density that I need. I should say that if I convert that cross-section into actual numbers, the cross-section that I need is 3 times 10 to the minus 26 centimeters cubed per second. That's approximately right over a fairly broad mass range in question here. That's sort of the target cross-section you're going for. And so what you want to do then is you simply want to vary. You only have one free parameter here, which is the mass of the dark matter particle. You vary the mass of the dark matter particle to get this cross-section. And what you find is that the energy density of this particle is roughly like so. Remember, h here is just the parameterization of the current Hubble constant. And so this is a number which is about 0.7. So this h squared is like a half. And so what you want is for a dark matter particle to be a little bit above a TeV in order to get the appropriate amount of dark matter. And there are a couple of comments that a couple of observations that are useful to make here. One is, note that this sigma v here is velocity independent. That's simply because you do an expansion, partial wave expansion, and the leading velocity term is the S-wave piece and is velocity independent. There can be higher terms that also could be relevant if the leading term is not important. But because you are non-relativistic when you freeze out, if there is a sizable S-wave piece, those higher order pieces tend to be not important. The second observation you want to make is that people talk about the WIMP miracle and talk about weak scale particles. But note that to get the actual appropriate amount of dark matter here, we're ending up with a dark matter mass which is more like a TeV. And this is fairly consistent, that actually the WIMP miracle kind of really looks like it more prefers slightly heavier mass particles. Now, that's not to say you can't have a lighter particle, well-tempered particles, but this is something that you often find, that heavier particles are better. Okay, so now we know the mass of this particle is roughly a TeV. So now you want to know whether this dark matter particle is ruled out. So how are we going to look for it? We're going to look for it in one of these direct detection experiments. So as an exercise left to the reader, the differential energy rate of scattering of a dark matter particle is this. So let's take a moment to actually work out and discuss what are the expressions in this here. So NT is the number of targets. So you'll have an experiment. It's going to have, say, a liquid xenon target, and you'll have so many kilograms of liquid xenon, and then the mass of the xenon is, say, 130 atomic mass units. And so that's how many xenon atoms you actually have in there to scatter. Mn is the mass of the nucleus of the thing that you're scattering off of. Rho chi is the local density, which is thought to be about 0.3 GeV per cubic centimeter. So we think there's about one, if it is a WIMP, you have about 1 WIMP per liter of space. Of course, they're moving extremely fast. They're moving at a velocity of 10 to the minus 3. So there's still a fairly high flux. M chi is the dark matter particle mass. This is the reduced mass of the WIMP nucleon system. Right? This is not the reduced mass of the WIMP with the nucleus, not with the xenon atom. This is the reduced mass of the WIMP with a proton. So in general, this reduced mass is approximately m proton. And the reason why you do that is because this sigma n here is the cross-section per nucleon. So you calculate the total cross-section off of a single nucleon, and then the idea is you can scale that up to think about any specific target. I should add, this is what is referred to as the spin-independent scattering, which is one that gets most of the focus. There's also spin-dependent scattering, but let's stay with spin-independent because that's where the parameter space of most anomalies live. So the idea here is that this sigma n is the cross-section per nucleon. You know what the cross-section to scatter off of an individual nucleon is, but because the momentum transfer of this process is relatively low, the WIMP sees the entire nucleus coherently. So you add up in the amplitude all of the scatterings, sum of the amplitudes off the scatterings of the protons as well as off the neutrons, assuming you have an FP coupling to neutrons and an FP coupling to protons and an FN coupling to neutrons. And you square this because it's coherent. Now, it's not completely coherent. Once you get up to these, the momentum transfers are roughly the size of the nucleus. So as you go to higher energies, this coherence will be lost, and that's captured by this here, which is the form factor, which is just the Fourier transform of the nucleus. And then lastly, you have the integral of f of v over v, which is where f of v is the speed distribution. That is the 3D speed distribution. I've averaged over all directions, and this is the resulting distribution of dark matter particles in the halo as a function of velocity. And you integrate from, since you're looking at the differential scattering rate at some particular energy, then you only have scatterings from dark matter particles with some minimum velocity. Only dark matter particles with some minimum velocity and higher are actually going to deposit that much energy in your detector, so you need to integrate over them. And this is actually a very good exercise to sit down and work this out for yourself, that this is the appropriate expression for this kind of a model to calculate its scattering cross-section. But you can see there's a lot of uncertainties in here. Let me give you a couple of references that are handy if you ever have to do some work on this. The first one is for the form factor. There's a nice reference by Duda, Gondolo, and Kemper. They just go through the different form factors, different ways people talk about form factors, where they get their data from. This is just a nice reference to have. They do a nice job of it. This speed distribution, a closed form of the integral for the speed distribution, can be found in Freese, Gondolo, and Savage. That's 06, 07, 14. Is that enough digits? That's not enough digits. Look for these people with a number that looks approximately like that. The usual assumption that is made is that the dark matter particles have some Maxwell-Boltzmann distribution, which is truncated at the escape velocity of the halo. So you characterize this distribution here by the local rotation velocity of the sun as it goes around the Milky Way, and some characteristic dispersion velocity, as well as some escape velocity. And these are the numbers that people actually use to characterize these things. It's not obvious that a Maxwell-Boltzmann distribution is the right distribution, and in fact, when you look at numerical simulations, there do seem to be noticeable differences from a Maxwell-Boltzmann distribution. Nonetheless, this is what everybody uses, and so if you want to compare the limits that are actually out there, this is how you can compare. And we'll discuss a little bit about that. The reason why I point you to this reference, although my pointing is incomplete, is that there actually are genuine errors, especially in some of the more prominent references in the closed form expressions for this quantity. So just be very, very careful. There are papers out there without erratas that have this expression wrong, and you will get a wrong answer. Questions about this? So what we want to do then is we want to calculate actually this process here for this canonical WIMP. And quite happily, we don't have to do it because Reuven Essig has done it for us, as have many other people. but Reuven has a nice discussion of electroweak WIMPs. I have the appropriate number of numbers now. And there you can find that the total cross-section, so that is not the cross-section per nucleon, but the total cross-section off of a nucleus, is this. Whoops. Which you now actually have to do sort of a backwards thing, right? Because you actually are really secretly interested in the total cross-section, but to go and use any of the exclusion plots, you need to convert this quantity into the cross-section per nucleon, so the cross-section off of an individual neutron. So you have to divide out, you have to replace this reduced mass by the reduced mass on the WIMP nucleon system, and then divide out by the total number of neutrons, or sorry, total number of nucleons in a given target. And so this obviously, since Z and A are going to vary from target to target, this is actually a bit of a lie because the cross-section for nucleon on, say, germanium is going to be slightly different from the cross-section per nucleon on xenon. And so when you actually use a limit plot to compare these experiments, you need to be mindful that this quantity, the cross-section per nucleon, does not actually exist for this model. It does not matter in this case. So the cross-section per nucleon is 2 times 10 to the minus 39 centimeters squared, approximately. So what are the current limits? I'm going to draw a bad plot later, and I'm going to start by drawing a more abbreviated bad plot now. But just so you know, this is the kind of plot that you have to get used to. So you put the cross-section per nucleon on the y-axis and the mass of the dark matter particle on the x-axis, and you get a shape that looks like this, where this is the excluded region. So you can understand what's happening here. As you go to low masses, this is the threshold. So any given experiment has some minimum energy that they can actually see scattering, see recoil. They can maybe not see a WIMP that with an energy below, depositing energy below, say, 3 keV. And so if you have very, very light WIMPs, it becomes exponentially unlikely, and in some cases completely impossible, for such a WIMP to deposit that much energy. And so when you go to low masses, you hit the threshold of the experiment, and you see this go vertical. And this is an extremely sensitive region of parameter space because you're really relying upon knowing how many very high velocity particles you have in your experiment. Yeah, or in your WIMP.
Formula is the threshold deciding the form factor?
The threshold is, so you're calculating dr der, so you integrate that or you do some other type of analysis starting at some particular energy. So you have energy dependence both here in ER and you have energy dependence in V min of ER, right? So this is actually, this function here is an implicit function of ER because once you get up to very, very high energies, the number of WIMPs that are around to scatter is very low. There can be additional types of models that have other energy dependence, but in this model, this is all of the energy dependence. It's in the form factor and the velocity integral. So at low energies, you're hitting this threshold. At high masses, what you're basically running into is that you actually know the energy density, and the number density is just rho chi over m. So as I go to, at very high masses, the reduced mass of the system reduces to just the reduced mass of the nucleus. So there's no kinematical dependence anymore once you get out to very, very high masses. So the only thing that changes is, I mean, the way you think about it, right, is that you no longer think of it as a WIMP coming in and hitting a nucleus. You should think of it as a very, very heavy stationary WIMP with a nucleus coming and bouncing off of it. And so the only change here is that as you go to high masses, the total number of WIMPs is just getting lower and lower. And so you have some point in between, which is where your experiment is best. And this tends to be in sort of the order of 50, 60 GeV. And so the current best limit has a minimum value at 50 GeV and has a cross-section of 2 times 10 to the minus 45 centimeters squared. And this is from the Xenon 100 experiment. And so this model, this dark matter model, this canonical WIMP, is just dead, 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 right? This point in parameter space would be way up there. So if I went out to a TeV, the 3 times 10 to the minus, or 2 times 10 to the minus 39 would be completely dead. So, but this is, I think, a very useful exercise about how to think about how you go about studying a WIMP. So you know one quantity, you know its annihilation cross-section. You use the annihilation cross-section to find out something about it, in this case, the mass. Once you know the mass, now you can also go and calculate the scattering cross-section and see how that compares to existing limits. And in this case, this model is excluded. Questions about this? Yes? You do have to chop it off the escape velocity. So it's implicit that this f of v here has some escape velocity in it. So there's some v above which this goes to 0. But formally, you do the integral up to infinity. Yeah. Other questions? I want to make a brief aside on neutralinos, because they're a very simple generalization of this. I'm not going to go into gross detail because most of their phenomenology from this perspective is pretty general. It's not specific to supersymmetry. But for the neutralino, you start with a mass matrix that looks like this. Okay, so I've drawn this not well. So you have 4 neutralino states. So you have the Beano mass, you have the Weino mass, and then you have the 2 Higgsino mass states. And this is down here is just the transpose of that upper 2x2 block. And what you used to have in supersymmetry was, as a very common point in parameter space, was that if you thought that this was solving the hierarchy problem, then the Beano mass, the Weino mass, and the mu parameter of the Higgsino should all be roughly of the order of the weak scale, in which case this is a very, very mixed up matrix. However, as time has gone on, and I should say SB here is sine beta, the ratio of the up and down VEVs in the 2 Higgs double model, and SW is the weak mixing angle. But as time has gone on and limits have, on average, pushed these quantities higher and higher and pushed the scale of SUSY breaking higher and higher, this off-diagonal piece is now much smaller than the diagonal piece. So you very often end up with something which looks very block diagonal. So you end up with a model which might be, say, very, very Beano-like. Or you might end up with a model which looks very, very Weino-like. Or you might end up with a model that looks very, very Higgsino-like. This is not necessarily true. There are definitely regions of parameter space where you can end up with a more highly mixed, well-tempered type of particle. But it is very common now that you end up into these sort of pure mass states. So the reason why I wanted to bring this up is not just to write down the mass matrix, but Also, to just make a comment about direct detection for neutralinos. Because if indeed this here is the block which just describes a pure Higgsino, so if I take these mass parameters and I make them very, very high, much higher than mu, then the dark matter particle that remains will be very close to pure Higgsino. But a pure Higgsino is just a doublet with plus and minus 1/2 hypercharge. So naively, you should say that such a particle should be very, very excluded because we just calculated the direct detection scattering cross-section and found out that it was 5 orders of magnitude higher than the existing limits. So why is that not the case? Well, it is actually because the scattering cross-section that we just calculated does not exist for this particle. So the scattering operator that we were talking about was Z exchange. And so Z exchange gives you some contribution that looks like this. And so when you integrate out the Z, you end up with an operator that looks something like this. Okay, so that's the interaction that one of the interactions that you can end up with. You also have an axial piece. But the important piece is that this here will vanish if chi is a Majorana fermion. Majorana. And so the case we were talking about before was a true Dirac fermion, and a true Dirac fermion can have this sort of vector coupling. But a Majorana fermion, this will vanish identically, and so you'd be left with axial pieces that either couple to spin, which is much, much smaller, or couple through what are called antipole operators, which are velocity and energy suppressed. And so it's just to be careful that when you get some nice intuition from a model like this, but then go to a nearby case, the dynamics can be very, very, very different. So as a consequence, neutralinos have their dominant interactions usually through Higgs exchange, which is several orders of magnitude smaller. Questions about this? Okay. In the remaining time, I would like to switch gears and just introduce you to the suite of anomalies that are motivating people to think about various dark matter scenarios. I'm not going to endorse any of these anomalies. I'm just going to tell you what they are, and I'm going to tell you how people are approaching them. So, loosely speaking, we have indirect anomalies and we have direct anomalies. So anomalies in indirect detection and anomalies in direct detection. So the anomalies in indirect detection, you have the Fermi Space Telescope. It's a gamma ray space telescope, and they have a galactic center bump. There's also the Fermi 130 GeV line, also in the galactic center. There is a excess of positrons generating a 511 keV line in the galactic center from integral. And then you have Pamela followed by AMS that see high energy positrons locally. Okay? Those are the indirect anomalies. I'm going to go through these in more detail. bless you. The direct anomalies that you have are gamma, which claims to see an annual modulation and has for some time. Cogent, I'm going to separate out the cogent modulation. Crest and CDMS silicon. I'm not going into details yet about what these particular things are, but these are all direct detection experiments that claim to see an excess of events beyond what they expected, and then the collaborations have different degrees of enthusiasm in interpreting those as dark matter. And I'll describe these in a second. So, what are they? So what I want to do is I want to take you through what the anomalies are and what are sort of the principal issues that dark matter models confront in trying to explain these. So let's start with the Fermi line. This is one of the more exciting ones, but it's also fairly uncertain. It hasn't been around for very long, and there are a lot of issues when you look at systematics that make people suspect, but until it's actually decided, I think it's still interesting. And so the idea is that if you look at the spectrum in the galactic center, you see some very nice spectrum until you get out to 130 GeV, where there is a sharp line. I'm totally overselling it with this drawing right here. It doesn't look anywhere that good. But that's how it's interpreted, and that's what it statistically looks like. And this was first pointed out by, really enthusiastically, by Venegar, but also Bringmann and collaborators, and Finkbeiner and Su. And neglecting the fact that the actual signal doesn't look this good, this is obviously very interesting because this is supposed to be one of the smoking gun signatures of dark matter, which is that you actually get a monochromatic line at the energy of the dark matter mass. You can also get this from a decay of a dark matter particle into 2 photons as well. So what is the big concern? Well, first off, the cross-section is high-ish. It's of the order of 10 to the minus 27 centimeters cubed per second, which is about a factor of 30 below your thermal cross-section. And this is naively higher than most models that people play around with get. More critically is what is referred to as the continuum constraints, which I will then just refer to as Lasanti et al., because she's the only one in the audience that I have to be sure to reference. But it's Cohen, Slatyer, Lasanti, and Wacker. And what they pointed out is that if you actually look at this spectrum in the inner galaxy, you see this nice line, but you don't see any deviations from a simple power law at lower energies. And most models that people tend to play with have something like this. You'll have, say, dark matter annihilating into W, and then you close that W loop, and you get the annihilation into 2 photons. And when you get that annihilation into 2 photons, it should come with an associated annihilation to W's, but when you annihilate into W's, those then should decay hadronically. They give you pi zeros. Those pi zeros give you photons, and so you should have some sort of a bump here at low energies that is not observed. And so you can actually place a limit on how large the ratio between these 2 diagrams is, and depending on whether you take their more conservative limits or their whether you take their more conservative limits or their more relaxed limits, they get that the ratio has to be less than somewhere between 10 and 100, very, very loosely speaking here. So you don't want, and this depends on whether or not you're actually trying to fit the shape here, whether you're just saying, I don't want to have too many photons, period. So this 100 is probably way, way, way too relaxed. 10 is maybe a bit stronger than you would 100% believe, but it's of that order. So the problem is that if this is a loop process, then the annihilation continuum is naturally orders of magnitude larger, and they studied this in SUSY models, and in particular found that the ratio in SUSY models varied from something like 200 to 500. So the problem of models generally then is that to get the gamma-gamma line, you have too much continuum. So then, of course, the solution is that you should get rid of this diagram. You should not have dark matter generating its annihilations into gamma-gamma through a loop of stuff you can annihilate into. But you could just have some other loop of other stuff. And as long as you can't annihilate into that stuff, it's fine. The only thing is that the mass of this mediator should be less than, call it about 300 GeV. So dark matter should interact with some charged particle, which is fairly light, and so you can see at the LHC. So that's the line. The next thing is the Fermi bump. It doesn't actually have a good name. I'm calling it the Fermi bump, but if you talk to people and you say blah, blah, the Fermi bump, they will probably not know what you're talking about. This has been emphasized by Goodenough and Hooper and Linden, Hooper and Slatyer, and Bazajian and Kaplingat. And so the idea is that if you go into the galactic center, there are various sources that you think should be there. There's a disk source that should be there. There's a stellar halo around the galactic center that should be there. And there's a point source around the galactic halo. And you should be able to subtract these things off by fitting them in different regions. And when you do that, you end up with a residual. That looks something like this. So a couple of points. The error bars out here are bigger. This is the residual. This means you take the total flux and you subtract off everything that's in front of you, and this is what you're left with. So this is the part that you cannot explain. So to get this, you really have to know what you're doing in subtracting things off, and that's the biggest criticism that people make on this. And the idea is that you can fit this with an annihilation of dark matter into stuff in the galactic center, and it's fit with, say, either, let me write it down over here. This is fit with either m chi around 10 GeV, where chi goes to tau tau, or around 50 GeV, where chi goes to BB bar. And then these things decay and produce pi knots that then give you gamma rays. The cross-section that you need is a few times 10 to the minus 27 for the lighter case. So these are totally kosher from sort of a thermal question. The distribution is appropriate for a dark matter halo, which scales like r to the minus 1.2 to 1 minus 1.4 in the galactic center. So the idea is that if you look at the density as a function of radius, there should be some spike as you move into the interior, and that goes like something like r to the minus 1.2. And the claim is that not only is this there, but that it's very hard to explain with, say, populations like pulsars, because if this steepness, if you think about this as a steepness, yes, it's r to the minus 1.2 or 1.4, but dark matter annihilates proportional to rho squared. So the actual fall off in the signal is falling off like minus 2.4 or minus 2.8, and pulsars, which are thought to be distributed in the galactic center, should not have such a steep profile. That is the claim that Hooper and Linden make, and I think Tracy Sletcher as well now. So let me take a moment to introduce a category of model that has gotten a lot of attention of late and is somewhat useful in at least applying to this particular anomaly, which I'll loosely call these things dark force models. And the idea is very simple. You have the standard model, which is SU3 cross SU2 cross U1, and you're very aware that, say, everybody has hypercharge, but not everybody is charged under SU2, and not everybody is charged under SU3. So you can add to this some additional dark gauge group that only dark matter is charged under. You imagine that this gauge group is broken, usually, and the simplest case is where you assume that G dark is a U1. It's simplest. If that's true, then there is a parameter that you can write in your Lagrangian, which is a kinetic mixing parameter that mixes this dark photon gauge kinetic term with hypercharged gauge kinetic term. Now, if you are at very high masses, if the dark photon's mass is roughly weak scale or higher, then it's appropriate to think of it as mixing with hypercharge. If it's lower, if m phi is of order GeV, then the dark photon mixes with electromagnetism. And an exercise that I will leave to the reader is to work out that all standard model particles acquire Q epsilon charges under the dark photon. This then allows you to have a lot of freedom in your phenomenology. In particular, the question of freezeout is largely separated from a lot of these other questions. So the early universe process of such models works where basically dark matter annihilates into these dark photons, and then the dark photons stay in thermal equilibrium through a process that looks something like this. And even though the interaction of this dark photon is suppressed by this kinetic mixing parameter epsilon, which can in general be very small, 10 to the minus 4, 10 to the minus 5, because you are competing against the Hubble rate, which is suppressed by the Planck scale, this process can keep the dark photon sector in thermal equilibrium. So this process keeps the dark photon in thermal equilibrium, and this process keeps the dark matter in equilibrium with the dark photons. The annihilation then is what happens is the dark matter annihilates into dark photons, which then propagate and decay. And so you can ask the question, well, what are the signals that you get out of the dark photon? Well, the dark photon's decay modes will depend pretty much just on its mass. So obviously, for light, dark photons, you'll have phi goes to E plus E minus. That's, if it's very light, that's the only thing that it'll go to. As you get heavier, you can go to mu plus mu minus. As you get closer to the rho resonance, so as m phi approaches m rho, you start getting a lot more decays into hadrons. And as you get up to higher masses, GeV and such, you get decays into hadrons as well. And so in this sort of GeV-ish mass range, you can have decays that will give you pi naughts, and those pi naughts can give you photons. So one explanation of this galactic center bump would be dark matter annihilating into dark photons at sort of the GeV mass, which then decay into these hadrons. You can search for these phis, and I have a very, very bad plot, but for the sake of time, I'm not going to try and reproduce it, but I can show it to people offline. And that there are experiments in Mainz, and there are experiments in Jefferson Lab that are going to be looking for these. APEX, dark light, heavy photon search, MAMI, these are the types of experiments that are looking for precisely these things as well as at the LHC. These dark photon models became very popular in the context of Pamela and Fermi. Pamela and Fermi were signals which are now confirmed by AMS that show a local excess of positrons. I don't want to dwell too much on this because I don't think it's a huge focus right now. So you had Pamela, and the only reason why I think that it's probably getting a sort of a second win now is that AMS has confirmed it, and what they confirmed is that if you look at the positron fraction, there was an expectation that they should drop at high energies. This is the expectation, just that ordinary astrophysical processes would produce fewer positrons at high energies. What was actually seen was a rise which now peaks at about 0.15 at a couple hundred GeV, which is what AMS sees. And the expected signal from most dark matter models was more like this. So to get this very, very large signal, you needed a model that would give you a lot of positrons and give you a very hard spectrum of positrons and not give you any associated hadronic modes, which were not observed. And so this sort of a dark force model worked in that you could annihilate into the dark force, which would then decay into E plus E minus and give you this very sharp rise. It had the added benefit that I won't discuss here of enhancing the low velocity scattering cross-section through the Sommerfeld enhancement, which actually brought your cross-section up to the needed cross-section. The reason why I want to skip that is because I don't want to give short shrift to the direct detection anomalies. Oh, and I should say, since I will be on a plane at 5:50, where would be a good place, Nima, for me to do Q&A over lunch? Here or in Bloomberg? Either one. In Bloomberg in the seminar room? So since I won't be taking off at 5:50, which means I'll leave here before the Q&A session today, anybody wants to ask further questions, just during lunch, I'll just hang out in Bloomberg in the seminar room on the first floor, and I can take Q&A there for anybody who wants to. So what is the situation with direct detection experiments? So this is my really, really bad drawing of the situation. So now I'm going to switch to color. So remember, every line here is an exclusion line. I'm drawing this really badly, but what I'm trying to be consistent with. That's a bit too rough. Okay. So, what are we looking at? This is the current landscape of direct detection anomalies. What are they? This is Dama, and this is Dama. This is Crest. This is Crest. This big yellow blob here is this new CDMS silicon result. And this red blob here is Cogent. So let me very quickly take you through what these anomalies are. And then you have lines here from xenon, CDMS, and CDMS silicon. This is CDMS germanium. So what are these? Blobs. What do you have? Well, let's start with Dama. Dama is a sodium iodide experiment. It's 250 kilograms. And what they look is they look for an annual modulation in count rate. So the idea is that here's your Milky Way. We are here moving that way. But if you zoom in on us, you'll see that the sun is moving like this, but then the Earth moves around the sun, as we are long aware. And so sometimes, because of the motion of the sun around the Milky Way, there's an effective wind of dark matter particles that is incident upon us. And then sometimes we move into the wind and sometimes we move out of the wind. So you expect a peak WIMP signal in the summer and a minimum in the winter. And this experiment has been studying this for about 10 years now, and off and on, and has gotten up to, depending on how you want to quantify it, around 9 sigma. And everybody completely believes now that there is a modulation in their experiment. There is no question there's a modulation in their experiment. The question is always what it is. You should be a little careful, because the usual reaction to this is to say, well, come on, lots of things modulate. The temperature modulates. The cosmic ray muon flux modulates. So why should I be surprised that this modulates? And it's actually a bit stronger than that, because they require it to be in the low energies, only in single-hit modulation, and a few other quality controls. So they have multiple detectors, and they want to see modulations in only one detector, not in multiple detectors simultaneously. So it's not as easy as that somebody out there has a very simple, straightforward, yes, that answers it conclusively type explanation for this. On the other hand, essentially the current set of dark matter models does not explain it well. Right. So Cogent is a germanium experiment, and they saw a spectrum of events, that looked like that. And initially, so this sort of flat background out here is understood. This peak is a particular radioactive isotope that's present in the detector that's gradually decaying away. And so the statement was initially that this exponential here was not something you could account for. Now they believe that they actually can account for about 70% of it as what are called surface events, events that are on the surface of the detector. Then, of course, people's reaction is, well, if you can explain 70% of it, then should I just think that that can probably explain 100% of it? That's the criticism. The other thing that Cogent claims to observe is they also claim, so you have this excess here, but they also claim modulation. And sort of marginal statistic significance, but they do claim one. And so that ends up with that pink circle in sigma m plot. I just realized that I did not put units on here, which is sin. This is about 10 GeV, and this would be about 1 GeV. And this cross-section here, question is about 10 to the minus 41, and up here is about 10 to the minus 40. You should, if you want the numbers precisely, I would encourage you to look at the real plots. So that's cogent. What about crest? Crest is a very confusing experiment. It's a calcium tungstate detector. These targets have very, very different masses. And what happens is that depending on how much mass, what target you have, different amounts of light are deposited in your detector. And so it's hard to isolate precisely where the signal is coming from because you don't know whether dark matter is scattering off the oxygen or the calcium or the tungsten. But they claim to have an expectation of around 30 events, and they observe around 60 events. And so they claim that that's a signal. More recently, that 30 comes from their modeling of their background, and some indications are that if they change the modeling of their background, they can absorb it. But that's this here. And then lastly, CDMS silicon. This is really one of the really, I think, critical situations where people say, what good are theorists? I think this is, well, we'll see whether or not this is of any use. CDMS silicon, CDMS is an experiment that has both germanium and silicon targets. Germanium is heavier, and so it's thought, and they have more of it, and so it's thought to be a better target to study used for looking for dark matter, and the silicon was mostly there as a cross-check. They stopped running this particular data set in 2008 and moved on to building super CDMS. But I like to think from unending harassment by theorists that they really wanted to see what the silicon data looked like, because silicon is a light target, and since it's a light mass nucleus, it's better for probing light WIMPs like these. They finally, just this year, in April, released their data set. And what they saw was 3 events with an expectation of about 0.7, depending on how you quantify it. And with the distribution that didn't look like their background distribution should look like. So they claimed that even though the Poisson probability of 3 events was not that high, the actual likelihood fit of 3 events was much higher. And so that was interesting. The only problem with all these anomalies is that when you look at this plot here, you can see that they all essentially lie on the wrong side of some line. And these are exclusion curves, right? Xenon, CDMS, especially xenon. And so there's a big debate as to whether or not that such anomalies even really could be dark matter. And like I said, I'm being agnostic here. I'm just showing you what the current controversy is. So there are essentially 3 approaches that you as a dark matter person can take to this. You can say the experiments are wrong. You can say the astrophysics is wrong. Or you can say your model is wrong. And those are essentially your approaches. There's been a lot of debate in the literature about whether the experiments are wrong. I won't go into that. There's been a big back and forth between whether or not the xenon experiments, which are these exclusion curves here, are really as sensitive as they say. They've put out a lot of information seemingly backing up that they are as sensitive as they say, but that is the debate. The astrophysics does not at this point seem to help you out. That's been pretty well studied. So at least if you're a model builder, your focus then moves on to thinking about these sorts of changes in models. So I'll just show one description of something like that that can help you out. So what is sort of the standard bag of tricks? That theorists currently have? Well, there are a number of things. You have inelastic endothermic scattering. You have inelastic exothermic scattering. You have momentum dependent interactions. You have spin-dependent interactions. You have, I'm going to refer to them as isospin dependent. So Fp not equal to Fn. And lastly, you have, not lastly, electron scattering. So these tricks that you might do will favor one experiment over the other one. So you look at a plot like that, and this plot is drawn under the assumption that you know how to compare these experiments. But once you break the rules of how your models actually work, these lines are going to move around, and maybe they move around in some fashion that this helps things out. So inelastic endothermic scattering, so dark matter scatters up into a heavier state. This favors heavy targets. Exothermic favors light targets. Momentum-dependent scattering favors experiments with high thresholds, generally. Spin-dependent interactions favor targets with spin. Not all nuclei have spin. This isospin-dependent coupling allows you to choose, in principle, Fp and Fn such that you can cancel off the scattering rate at one particular target. So if you look up there and you say xenon is your nemesis, you can then choose that to kill one target. And electron scattering, well, like I said, most of these experiments look for nuclear recoil, look for the recoil of the nucleus. Some of them don't care whether it's electrons or nucleus. So electron scattering just favors non-discriminatory experiments, like Cogent and Dama. So you can build actually a fairly simple model. For instance, using this dark force setup, I'll focus on just one. I'll focus on this. And if you have a dark photon, then that photon should couple to a Dirac fermion. But once this gauge symmetry is broken, those two states in the Dirac fermion can become pseudo-Dirac, and so this can be split into a chi star and a chi. So your spectrum looks something like this. So here's 0. You have some Dirac fermion, which is split into chi star and chi. And if you calculate the lifetime of an excited state through such a dark photon, the lifetime can be much, much longer than the age of the universe. So what this then allows you to do is that when you downscatter, you have a little bit of extra energy that can give a kick to the nucleus, and it's going to give a greater kick to a lighter nucleus. And so, in particular, most recently, this was studied by Franzen et al. And they find that a m-chi of approximately 5 GeV and a splitting of approximately minus 50 keV can explain the CDMS results versus the xenon results. So this is just an example that, you draw that plot and it looks very, very convincing that everything is ruled out. Then you reinterpret it in some other model context like this, where dark matter comes in, downscatters, giving a kick to the nucleus, and maybe some windows open up. So that's not enough time really to discuss the anomalies. They can go on, I can go on and on and on, so maybe it is good that I don't have time to discuss it. But let me make one comment about this, because right now, just to conclude on this, right now, when I look at that plot and I look at the models and I go into detail on it, I find it personally to look very, very daunting, that it's very, very difficult to get all these experiments to really be reconciled. Maybe one of them is right, maybe none of them are right, but I find it actually a real challenge, given the huge amount of data that we have now, to get these things to agree with each other and with the null results. However, in 2001 or 2002, I can't remember, but I remember going to a conference and I went to a talk by somebody who I will not say who it is because this is being recorded. But it was a very respectable person, certainly more respectable than I am. And he said, you can go through, he was talking about Dhamma, and he said, and you can go through it and you can look at absolutely every single possible scenario you can think of, and none of them are going to explain how to reconcile Dhamma with the existing constraints at the time. And it was just a full stop. There is no solution. This is an excluded scenario. And that was in 2001, 2002. And in the decade or so since then, there have been a huge number of new models that precisely do that, that do reconcile Dhamma. Maybe now it's hard, but my only point is that it's not always obvious what is a failure of the experiments and what is a failure of our creativity. So even if I can't come up with a good explanation right now, that's not to say you can't come up with a good explanation of how to make this all make sense. So I will stop there. Thank you for your attention. And I'll be in Bloomberg during lunch if you want to talk. Questions